Lesson 14. Inductance. Section 14.3. Mutual inductance. There are two coils. The left coil is coil 1, and the right coil is coil 2. A voltage V1 is applied to coil 1 and a current I1 flows. The direction of the magnetic flux of density B1 follows the right-hand screw rule. Some of the flux passes through coil 2. The magnetic flux linking coil 2 can be calculated using the surface integral of B1 across the area S2. This flux is denoted by phi21. According to Faraday's law, the induced voltage V2 of coil 2 is given by this equation, where N2 is the number of turns of coil 2. The mutual inductance M21 is defined as the coefficient in this relationship. The unit is Henry. The mutual inductance M21 can also be defined by this equation. The mutual inductance is reciprocal. Suppose this torus is made of ferromagnetic material. The radius of the torus is uppercase r meters, and the radius of tube is lowercase r meters. For example, the relative permeability of iron with 99.8% purity is 5000, which is very large compared to that of air. A toroidal coil with N1 turns is wound around the iron torus. This is coil 1. A current of I1 amperes flows through coil 1. Due to the high permeability of the iron core, most of the magnetic flux generated by I1 is confined within the tube. Another coil with N2 turns is wound around the same core. This is coil 2. Most of the magnetic flux generated by coil 1 passes through coil 2. The magnitude of the magnetic field intensity H at the center of the tube is given by this equation. By assuming that the magnitude of H is uniform across the cross-sectional area of the core, the flux linkage of coil 2 is expressed by this equation. Thus, the mutual inductance between the coils wound around an iron core is derived as shown in this equation. Exercise 14.3.1. Pause the video, and answer the problem. Find the mutual inductance M between the rectangular line conductor and the infinite line conductor. The answer to exercise 14.3.1. Pause the video, and check the answer. Exercise 14.3.2. Pause the video, and answer the problem. Find the mutual inductance M between the two coils. The answer to exercise 14.3.2. Pause the video, and check the answer. Exercise 14.3.3. This is your homework. Pause the video, and answer the problem. Exercise 14.3.4. This is your homework. Pause the video, and answer the problem. Section 14.4. Energy. Let's see how much energy is stored in an inductor. The inductance is denoted by L. The directions of V and I are defined as shown in this figure. The relationship between V and I is given by this equation. Then the power P inputted into the inductor is V multiplied I, and V is replaced with the above equation. Therefore, the energy stored in the inductor is derived by integrating the power over time, and the result is 1/2 times Li squared. Exercise 14.4.1. Pause the video and solve the problem. Find the energy stored in the solenoid coil per unit length using the two different approaches. The answer to exercise 14.4.1. Pause the video, and check the answer. Exercise 14.4.2. Pause the video, and answer the problem. Pause the video and check the answer. The internal inductance L equals mu over 8 pi is derived using the energy stored in the conductor. Exercise 14.4.3. This is your homework. Pause the video, and answer the problem. The author of this material is Takeshi Furuhashi, Professor Emeritus, Nagoya University. If you have any questions, send emails to this address.